Hello everyone, my name is Joe Scorson, channel is called Ethernet Link, and in today's video we got another C++ kind of vibe going on. I'm going to explain another C++ script. I've been enjoying making them and learning things about the language. I hope that you guys enjoy watching them. The last video on C++ got a lot of views from me, so we're going to keep on going with it. We got a little bit of a setup going on, I guess you could say. Still the same actual setup, laptop, camera, headphone, microphone. But you know, we got the blue going on. I got this awesome theme in VS Code. So we're going to get a little theme going on whenever I code these videos. I don't really code much Python in C++, or in C++. I don't really code much Python in VS Code. Whenever I do, I'll change the theme. We'll get it going. At least these lights will change. I don't know about you guys, but in my mind, C++ is this icy blue. Python's like orange or red. Like JavaScript is green. Java is like yellow. Maybe, you know, that sounds right. It's like how in school, like the notebooks for each subject, you know what I mean? Like science is green, global or history, whatever's blue. You know what I mean? What was your color combination? Tell me in the comments. I'd love to see them. I'm the kind of guy now in college, I use just one huge, like 5 subject. Normally just like 1 or 2 subjects takes up like three sections of that book. You know what I mean? That's what happens when you take a lot of math courses. Regardless though, enough of me rambling. Let's get into the video then. So, I think this topic is awesome. Maybe it's just the nerd in me. But we're going to be pricing options in C++ using a Monte Carlo simulation. I know I put beginner friendly in the title. It will be beginner friendly. I don't care if you know nothing about a Monte Carlo simulation. You're going to understand what I'm getting at by the end of this video. We're going to get it. We're going to get you right. I don't care how much you know about it. You're going to learn something. And we're going to start not at all in VS Code, but with this link I found. I'm going to put it in the description. But I think it explains how you can use Monte Carlo simulation to estimate something, right? So, I'm going to read this, then we're going to watch it for a little bit, and then we're going to go into the code. So, a Monte Carlo simulation relies on a repeated random sampling of objects from a distribution and subsequent operation of them to generate numerical results. In this simulation, we utilize random sampling of 2D points of a uniform distributor to estimate the value of pi. The circle has a unit radius, whereas the square has a length of 2 distance units. If the points are appreciably random, and if we have generated enough number of points, then we go into this formula, the number of points inside this circle over the total number of points, everything, is close enough, almost equal to about the area of the unit circle over the total area, which is again close to pi over 4. So then pi is about 4 times the total number of points inside the circle and the total number of points. So if we keep on going, we can see all these random points being generated within this confine, and then it estimates the value of pi. And it'll get close. The longer you do this, the closer and closer it would get to 3.1415, whatever. And then a little note down here, after about 1,000 points that have been sampled, the estimated value of pi usually ranges between 3.12 and 3.16. So we're going to let this, it's going back up now. It's wiggling around. You can see 3.19, 3.18. There comes a point where it just all of a sudden starts to get really close. We'll see if we can make it. I'm not going to make you watch this that long. I'll put the link to it in the description. So let's get into the code now. Cool. I'm going to get my little script up, and we're going to go through. First of all, let's talk about what we're actually trying to do with this pricing and option with a Monte Carlo simulation, with that random sampling mumbo jumbo there. So, when you price an option, I'm going to refer to the Black-Scholes model with this. The Black-Scholes model is an option pricing model. What does that mean? When you have a stock price and the strike price, and you know the risk-free rate of that, volatility of it, and when that option will expire, you can price an option. An option is the right, but not the obligation, to buy or sell 100 shares of a specific stock on a specific date on a specific strike Actually, you can exercise them early, but we're not going to get into that. And buy or sell respective to call or put option. Right? Now, let's say, right, our initial stock price and our strike price are right here. Say our strike price is still $100. So I have the right to buy 100 shares at $100. And then all of a sudden, the stock price goes to 110. That contract, that agreement I have with whoever to buy these shares at $100 just became a lot more valuable, right? So that's how you trade options pretty much. That's why options appreciate and depreciate, is how attractive is this agreement right now is actually what trading options is. So how do we price that? That's very hard. There's a lot of discussion about it, because right now, whenever you open up your phone, you go on Robinhood, you go on TD, whatever, or Schwab now, whatever you use, the option prices that you see are from the Black-Scholes model. And if you've ever read this book, you know that it's inherently wrong. It is wrong for a few reasons that we're going to get into, but it's a good guess. And the reason that we use it is because it's easy to use. Easy to calculate when you make these assumptions, these kind of agreed upon misfortunes, I guess you could call them, in the pricing model, to make them simpler and make it less of a headache. Just simply spit you out a price, regardless of how accurate it actually is. So let's first go over these helper functions. Then we're going to go through our main, and then we're going to go over the Monte Carlo pricing function. So now this function, I'm not going to go through line by line because I feel like that would be a bit of a waste of time. It's not really what this video is about. But all this function does is every time you call it, I get a random number with a mean of whatever and a standard deviation of whatever. It's on this random numbers in that distribution. And then we just return that number. Simple enough. In the example, in this, we use 0 and 0 as the mean and a standard deviation of 1. Why? This random number represents a percentage move of the stock. In a perfect rational world, there will be a lot of little moves and not a lot of big moves. We know that not to be true because I believe that there was the example of Citigroup trading dollar-yen spreads in the 1970s, 40s. And there was a big move in the yen. It was minus 9.2%-ish. It's in that book I showed you, The Misbehavior of Markets by Benoit Mandelbrot. That big move down in the yen, if you were trading since when the Big Bang allegedly happened, if you're trading since then, you still shouldn't have seen that move. In all those billions and billions of years since that alleged event, you still should have never seen that happen, yet there it was, right there. So that nullifies this whole notion of the market having a normal distribution. We know that it doesn't. We know that the market is skewed to either direction, whether the position of the market is long or short. Think about it like this. The S&P 500 and the NASDAQ, yes, it goes up because earnings grow, but regular people just buy it. It's inherently long. Something like copper futures. The position of that market can either be long or short, because who trades futures contracts? People that have a lot of money and are very confident trade futures contracts like that, right? So when a number of people, hundreds of millions of people every day buy the SPY ETF, how many people buy a copper future? Right? It's way less. And so when most of the people buy copper futures, then the position market's long. Most of them sell it short at the position of the market is short. We know that to be the actual way it happens, but this notion that we have of random or normal distribution says that each price point is independent of the last, and that the percentage moves should fall on this normal distribution. We know that not to be true, yet, like I was talking about before, this is one of those exceptions that we make to make this pricing model convenient, let's say. So, bottom line, this returns a random number on this distribution. So now, let's go through And also, whenever you see European call and put option, Black-Scholes priced options are considered European. So, function to calculate the payoff of a European call option. Great. So you'd have a double S, a number represented S, and then K. K would be our strike price, and S would be the stock price at a given point in time. So like I said before, if this goes to 110, I make $10 a share for my agreement with you. I make $10 a share because because my strike price is 100. The stock price is at 110, so I could buy shares at 100. I just made $10, right? So that payoff is that price minus the strike price. And if it's greater than it, like it is here, we see we make $10, whatever. Or I went backwards. And so for calls I'm talking about. And for puts, if this was $90, then we would make the money. Okay, cool. So now, Joe, why does this say max here, right? We can lose money. Absolutely. However, we're pricing the options. What does that mean? That means that the price can't be below zero. You're not going to get a credit for buying something. I'm not going to pay you for buying something. So that's why we floor it at zero. If it would be a loss, we're just going to add zero to our average. If it would be a gain, then we'll use that. But this option price can't be below zero. If not, that would be the easiest no-brainer buy in history. I don't care what direction the equity I think it'll go. I want some of those calls because that's just incredible value. So we can't have them be negative. Next, though, let us go into the whole engine, right? The big V8. So we have all of our variables from before. We have our initial stock price, S of 0, our strike price, risk-free rate, our volatility, time to expiration, number of simulations, and a call, and if it's a call option or not. Now, another fun thing to do, if you care enough, is to make these two things dynamic for every simulation. We know that the volatility and the risk-free rate of a stock is not constant over the whole life of the option. So another cool thing to do would be to use a distribution that is not normal and to make these two numbers dynamic, if you so care enough. Regardless, though, let's keep on going through this. So we have our payoff sum, because we're going to find an average, right? So we're going to add up everything from these functions, right? We're going to add up everything from this calculation, stored in this variable, right? So now for every single one of our simulations, we're going to iterate through whatever this number is. In this example, it is 100,000. So we're going to iterate through that. And so now what this is, generate a random price path. What this does is it estimates the stock price at the maturity of the option. So we use this formula, the initial price times, and then this represents Euler's number raised to, and separated in these blue parentheses. So Euler's number raised to the risk-free rate minus 1/2 times sigma squared, right? Sigma squared times the time to expiration plus sigma times the square root of t, time to expiration, and then times our random number percentage move. And that is a random price path for how much the stock should move according to this normal distribution. So now if it's a call option or not, we would calculate the payoff. So our price at maturity and our strike price, like that concept I explained to you earlier, with the 110 or not. On calls, we made $10 a share. On puts, we lost $10 a share. So with that concept in mind, we're going to add whatever payoff we get here to our payoff sum. We're just going to keep on adding up. And then our average payoff is, of course, the sum over how many iterations. And then we return the payoff sum discounted to a present value, because we want to know what the option will be worth right now, because we're trying to see if it's a good deal pretty much. So this is Euler's number raised to the negative risk-free rate times time to maturity times the average payoff. So now to recap on our the parameters, we have the initial stock price, strike price, risk-free rate, volatility, time to maturity, number of simulations. So we want to know a call price, so we're saying that it is a call. Put price, we're saying that it's not a call. And so now we just have to get our values and put them through. So if we open up a terminal and we're in the right directory, you would need to say G++, whatever the name of your file is, -O, and then whatever you want to call your output file. I just called it Monte Carlo option pricing out.exe. So you'd run that command. Then you would just type in the name of this file, click enter, and there you go. You get your values. Now, Joe, we discounted it to present value to know what it'll be worth now. Why can't we just see what it'll be worth later and see if it's a good deal? You're absolutely right. So now if we were to do that, again, recompile it, right? We see that the average payoff, we should make 50 cents, 53 cents on our put on our calls, and what is that, 20 something cents on our puts in a year. And so it'll be up to you to decide how much you would, if how good of a risk that would be. Because ideally, you would know that you're risking $10.34. We know that with option prices, it's we multiply this by 100. Excuse me, by 10. Am I tripping? No, by 100. So this what you would actually pay for this contract is $554. Yes, that is correct. So you would risk $10.34 or $1,034 to make a couple $100. So you would have to decide if that risk was worth it. But that is totally a way to do that. That's the video. That's what we're doing. I hope that you guys found this video informational, and it helped you get a grasp on pricing options and the nuances in it, because it is voodoo. Option pricing models are the biggest just, all right, let's go with it, ever. If you can build something that values options more efficiently than the Black-Scholes model, make money with it for 4 decades, publish it, win a Nobel, and go drive Aston Martins all day. I would drive Aston Martins when I was still making money with it too, but that's what I would do. But option pricing models is one of those things where, how do you know you're right? It's a pricing model. At the end of the day, it's worth however much someone's willing to pay for it. But you still need that point in time, because it is a derivative, right? At any point, if I have these variables, at any point I should be able to tell you what this contract is worth, set in stone. If you're willing to pay more or less, that's the market's own decision, whether it's good or bad. But that's how much this contract is worth. And so you should be able to tell, is this contract over or undervalued? The risk-free rate should also be able to change, right? We just went through a Fed hiking cycle. Volatility should be able to change. Things happen. And that's why sometimes you get those massive options payouts, because this normal distribution doesn't account for them. So when that big move comes, that's when you get the fat tails, as Mr. Mandelbrot, doctor? I'm not certain. But that's what Mandelbrot was talking about. These models, they don't account for those fat tails, those big moves. And that's what we need to account for as traders, as quants making these pricing models, mathematicians, computer scientists, whatever you want to call yourself. But yeah, I'm going to put a link to this code in the description in the GitHub. I'm going to put a link to this cool little simulation in the description. I'm also going to put a link to my company. It is called Prometheus Analytics. I think I actually have my trading view open right now. I do. So you can take a look at a recent indicator I made, this reversal script. You can see it plots reversals on the screen. No, you can't know how I did it. Closed source indicator. But you're more than welcome to get a subscription and use it for as long as you'd like. Even if you only buy this indicator, you would also get access to our Discord where you could get alerts from this indicator, but you can't use it. These things work on any time frame, any assets, and yeah, I don't know what else to say about it. I thought I had another thing in the pocket, but the link to this will be in the description. The link to my personal Twitter will be in the description, and the link to the business Twitter will be in the description. I hope that you guys enjoyed this video, that you subscribe and like the video and stick around for another one. If you guys have any ideas for videos you want to see, let me know in the comments. I'm thinking my next one will be about the correlation trading in stocks. So kind of like pairs trading, buying. So I want to go long bonds. Let me also go long oil because they should move inversed, and I think I'll make money on both of them. Is kind of like what correlation trading is like, pairs trading like that. Buying two things that move inverse, hoping you make money on both. But I hope that you guys enjoyed this video about options pricing. It was a lot of fun to make. I think that things like this are really cool because it's just, how do you know you're right? You never do unless you make money. So get out there, have a good time coding. Let me know any ideas you have. And yeah, hope you have a good one. Goodbye.